This is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. And in fact, in our previous lecture, lecture 16, we introduced the idea of a derivative, the primary object of study in Calculus 1. The derivative of a function f of x is another function, f prime of x, defined in terms of a certain limit, and it's defined in such a way that it gives us slopes of tangent lines to the graph of f of x. As you've seen, computing a derivative of a function with the limit definition can be fairly complicated, and sometimes it's prohibitively complicated. The good news is that there are certain rules for finding derivatives that allow us to bypass the limit in many situations. So that's the topic of today's lecture 17, rules for derivatives. Of course, this builds on what we had before, so let's recap the previous lecture. We had this very important idea of the derivative of a function f of x. It's another function, f prime of x, defined by the rule f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. So when you plug in an x to f prime, the value you get for an output is the value of this limit for that particular x. You take the limit as h goes to 0 of this quotient. We saw that alternatively, we could write this as the limit as z approaches x of f of z minus f of x over z minus x. And whichever limit you use, you get the slope of the tangent to the graph of f of x at the point x f of x. So the picture is this. You've got the graph of f of x. Pick an x value. Look at the point x f of x on the curve. Take the tangent line to the curve at that point, and its slope is going to be f prime of x. That's a function of x because the slope of that tangent line depends on the x that you choose. Notationally, f prime of x is also denoted as y prime, or dy dx, or ddx of f of x. This notation, ddx of f of x, it means take the derivative of f of x. And it stands for the derivative of f of x, or f prime of x. We're going to do a quick example to set the stage for today's discussion. Suppose f of x is the function x cubed, and we want to find the derivative f prime of x. We can use this definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now when working out this limit, you've got an h on the bottom, it's approaching 0. So you're hoping to cancel this h on the bottom that's turning to 0. But let's see what we can do. Up on the top, we have f of x plus h minus f of x. And remember, f is the cube function. Whatever gets plugged into f, you cube it. So on the numerator here, the f of x plus h is x plus h cubed. And the minus f of x is minus x cubed. So now our limit looks this way. Well, let's see if we could collect some like terms on the top and maybe cancel the h on the bottom. That's going to involve our cubing out the x plus h. This is x plus h times x plus h times x plus h, and you have to FOIL all of that stuff out. And you've probably done this before. I'll skip the gory details, but when you cube out x plus h, you get x cubed plus 3x squared h plus 3xh squared plus x cubed. And the pattern there is the powers of x decrease, x cubed, x squared, x to the 1, x to the 0, where the powers of h increase, h to the 0, h to the 1, h to the 2, h to the 3. And you have these coefficients that you pick up as well. But all of this in parentheses is the expansion of x plus h cubed. And we're subtracting off an x cubed. If you look at what we have here, we've got an x cubed at the very leading term, and then a minus x cubed. So those are going to cancel out. And what are we left with? The limit as h approaches 0 of 3x squared times h plus 3xh squared plus h cubed over h. And now we can attain our goal of canceling this h at the bottom because every term on the top has an h in it, and we can factor that out. We get the limit as h approaches 0 of h times the expression 3x squared plus 3xh plus h squared. In each one of these terms here, an h came out. And now h's on top and bottom cancel, and we have this really nice limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now in this limit, x is just, it represents a number. It's h that's going to 0. And we have two terms here, the 3xh and the h squared, that have an h in them, but this one has no h. So as h approaches 0, the 3x times h gets closer and closer to 0. The h squared turns to 0. So what we get is 3 times x squared plus 3x times 0 plus 0 squared. And that's 3x squared. So in conclusion, if f of x is x cubed, its derivative is the function 3x squared. So we have d dx of x cubed is the function 3x squared. So that's fine, but you can imagine that if your function x cubed was more complicated, like even x to the 5th, or even more complicated than that, a polynomial or something, this limit would get really messy. So to remedy that, today's goal is to find rules for derivatives that avoid limits. One of the big rules that we're going to come up with today is called the power rule. In fact, that's the first thing we'll do, and it's going to tell us what the derivative of a power function, x to the n, is. And I'll give you a little sneak preview. Here it is. The derivative of x to the power of n turns out to be n times x to the power of n minus 1. So the derivative of x to the 3 is 3 times x to the power of 3 minus 1, or 3x squared. So we're going to spend some time developing this rule. And I want to point out here, and that saying d dx of x to the n equals this expression, we've totally bypassed the limit that we had to work out here. So we're going to quickly derive the power rule, this rule in blue, but there's a little algebra we have to tackle first of all. We'll derive the power rule working out a limit very similar to what we did here. And here we had to expand out x plus h cubed. And you can imagine that if the power that we were differentiating was x to the power of n, what would happen here would be x plus h to the power of n. And that could get pretty complicated. So the first thing we're going to do today, with an eye towards that goal, is to review a little bit of algebra. I want to talk about how to expand x plus h to the power of n, where n is an integer. When n is a small number, like 0, say, it's easy. X plus h to the power of 0 is 1. X plus h to the power of 1 is just x plus h. What about x plus h squared? Oh, that's easy. You FOIL that out all the time. It's x squared plus 2xh plus h squared. To get x plus h cubed, you'd multiply x times h times this x plus h squared, and in collecting like terms, you get what we had on the previous slide. X plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed. Maybe you haven't done it for a while, but FOILing out x plus h to the power of 4, x plus h times itself 4 times, this is what you get. You can look at this as, you could take x plus h cubed, which is this, multiply it times another x plus h, FOIL it through, distribute it through, collect all the like terms, and you get x to the fourth, 4x cubed h, plus 6x squared plus 4xh cubed plus h to the fourth. Now the pattern here is that, and it's typical for all of these powers of x plus h, you start out with x to the power of what your n is, x to the power of 4. Then you get a 4x cubed h. And the powers of x in each term are going to decrease. X to the 4, x to the 3, x to the 2, x to the 1, x to the 0. Whereas the powers of h increase, h to the 0, h to the 1, h to the 2, h to the 3, h to the 4. The total degree of each term is 4. X cubed times h to the 1, the 3 plus 1 is a 4. And you pick up these coefficients, 4, 6, 4. If you work out x plus h to the 5th, it turns out to be this long expression, starting with x to the 5th, and the next term is 5x to the 4 times h, and then 10x cubed h squared, and so on. You may be a little bit rusty on these coefficients, the 5, the 10, the 5, but let me remind you of where those come from. You probably saw in algebra Pascal's triangle. It's an infinitely tall triangle, as indicated here, and on its two sides it's got 1s going straight down forever. But then for the other terms, for any number in the triangle, it's going to be the sum of the two numbers above it. So right here we get a 2 because 1 plus 1 is 2. Right here we get a 3 because 1 plus 2 is 3. A 6 here because 3 plus 3 is 6, and so on. And with that rule, you could carry this triangle out forever. But the important thing about Pascal's triangle for us is it gives us the coefficients for x plus h to the power of n. You just look at row n for Pascal's triangle. For example, x plus h to the power of 5 has coefficients 1, 5, 10, 10, 5, and 1. And those are the coefficients, or the numbers from row 5 of Pascal's triangle. Likewise for x plus h to the 4, the coefficients are 1, 4, 6, 4, 1. That comes from row 4 of Pascal's triangle, 1, 4, 6, 4, 1. Now you may be a little bit rusty on this, and if you are, that's okay. It's not going to hurt you. The important thing here for us is the pattern that we're getting here. X plus h to the power of n, it has an expression that looks like this. It starts out with the first term as being x to the power of n. The very next term is n times x to the power of n minus 1 times h. For example, when x is 5, the second term is 5x to the 4, h. When n is 4, the second term is 4x cubed, h. When n is 3, the second term is 3x squared, h. The second term is always n times x to the power of n minus 1 times h. Now the next term, it's got some coefficient, 3, 6, 10. Let's just call that coefficient a. It's a constant. It's multiplied by x to the power of n minus 2, 1 less than we had here, then times h squared. So the power of h goes up from the previous term. Then we have a coefficient b times x to the power of n minus 3 times h cubed. And that pattern just keeps going with coefficients. Next one is c. But the powers of x go down, the powers of h increase, until at the very end, the next to the last term is n times x to the power of n times x times h to the power of n minus 1, and the very last term is h to the power of n, as we see here. So this was our quick algebra review. It tells us the structure of x plus h to the power of n. So what's in this blue box? We're going to use in just a second when we derive the power rule. Here it is. The question we're concerned with is, if f of x is x to the power of n, then what is f prime? What is its derivative? Well, let's get to work on that. The derivative f prime of x is given by its definition. It's the limit as h approaches 0 of f of x plus h minus f of x divided by h. And the f of x plus h in this limit is x plus h to the power of n. That's our function. F of anything is that to the power of n. So f of x plus h is x plus h to the power of n. And then we have a minus f of x, and f of x is x to the power of n. So f prime of x is going to be the value of this limit. On the previous slide, we talked about the structure of x plus h to the power of n. It's x to the n plus n times x to the n minus 1 times h times some coefficient a times x to the n minus 2 h squared plus some other coefficient b times x to the n minus 3 times h cubed, all the way down to nx h to the n minus 1 plus h to the n. That's all of that in parentheses is x plus h to the power of n expanded out. And then we have a minus x to the n way over there. I've been kind of hazy about what these coefficients a and b and so on are. It turns out we don't need to really know what they are because they're going to disappear in this limit. In fact, if you look at this, you have two like terms, x to the power of n and minus x to the power of n. So those are going to cancel out. And look at what we get. What's on top is all of this other stuff. N times x to the n minus 1 times h plus some number a times x to the n minus 2 times h squared plus some number b times x to the power of n minus 3 times h cubed, and so on, all the way down the line to h to the power of n. But the important thing to recognize here is that every single term on the top has an h in it. So you can factor that h out and cancel with the one on the bottom. The h comes out of the top, and you'll notice that in the expression in parentheses here, the first term, n times x to the power of n minus 1, it came from here where there was an h to the power of 1. So this term doesn't have an h in it, but every other term coming from the terms that had higher powers of h up here has an h in it. So when we do the cancellation, we have the limit as h approaches 0 of our first term, n times x to the power of n minus 1, plus a bunch of other terms that have h's in them. And here h is going to 0, so all of those other terms, they turn to 0. And all we're left with is that first term, n times x to the power of n minus 1. So the answer to our question, what is f prime of x? F prime of x equals the function n times x to the power of n minus 1. That's called the power rule. The derivative of x to the power of n is n times x to the power of n minus 1. And class, now that we've worked out this limit to find the derivative of x to the power of n, we'll never have to use this limit again, to do this limit again for this particular function, x to the power of n. we're just going to remember the rule. The derivative of x to the n is n x to the power of n minus 1. Now that you've seen it derived, you have license to use it, and you'll use it a lot. Let's look at some examples. So here's our power rule. The derivative of x to the power of n is the function n times x to the power of n minus 1. For our first example, let's do d dx of x to the fourth, the derivative of x to the fourth. According to the power rule, we bring down the power 4 and multiply it times x to the power of 4 minus 1, or just 4x cubed. So the derivative of x to the fourth is the function 4x cubed. Now let's pause for a moment and see that that makes sense. Think about the graph of x to the fourth. It's this sort of, looks like a flattened out parabola. That's the function we're differentiating. And we just found out that f prime is 4x cubed. I'll do that in blue. The cube function looks something like this. So here we have the graph of the function x to the fourth and its derivative 4x cubed. Look at the graph of f of x. Over here the slopes are negative and the derivative is negative. Right here at the origin, the slope is 0, the derivative is 0. And when x is positive, f of x has positive slopes, and sure enough, the derivative is positive. So it certainly meets our expectations for doing what a derivative should do. We know, in fact, that this derivative gives us exactly the slopes of the tangent lines to f of x. What about the derivative d dx of x to the power of 100? Well, you certainly wouldn't want to use a limit for this, but look how easy it is to get this answer using the power rule. It's just 100x to the power of 99. There's our derivative. So it's a very easy rule to apply. It's so powerful. It simplifies finding derivatives of powers immensely. I should point out that when we derived the power rule, we proved it assuming n is a positive integer like 1, 2, 3, 4, and so on. Later on, we're going to see that this power rule works for any real number n, not just integers n. And although we haven't verified that yet, I'm going to take the point of view for now that it's okay to use this fact for now. We're kind of going out on a limb when we do this, but it all works, as we'll see later. So for example, if you have the derivative of the square root of x, that's the derivative of a power, x to the power of 1/2. The power rule says that your answer, your derivative, is going to be 1/2 times x to the power of 1/2 minus 1. That's applying this template here. That's 1/2 x to the power of negative 1/2 when you subtract 1 from 1/2 here. That negative power of x can go down to the bottom, 1 over 2 x to the 1/2. And that's 1 over 2 square root of x. So notice that by using the power rule, we very easily found the derivative of the square root of x, 1 over 2 square root of x. And you'll remember from our previous lecture, we actually computed the derivative of this function square root of x with the limit process. And remember, this is exactly the answer we got, 1 over 2 square root of x. Look how much easier this is with the power rule. For another example, suppose f of x is 1 over x. Let's think about f prime of x. Well, go back to f of x. 1 over x is x to the power of minus 1. It's a power. So we can find the derivative f prime of x using the power rule up here. We bring down the power of minus 1. So minus 1 times x to the power of, and then we subtract 1 from the power of minus 1. So minus 1 x to the power of minus 1 minus 1. And that's minus 1 x to the power of minus 2, or negative 1 over x squared, bringing the negative over. So the derivative f prime of x is the function negative 1 over x squared. And again, you'll remember that perhaps that we actually computed the derivative of 1 over x, this function, using a limiting process, using the limit definition of a derivative in our previous lecture, and we got, after a page of limits, negative 1 over x squared. So now that we've invested the time to establish the power rule, it allows us to find derivatives very, very quickly, as long as we're taking the derivative of a power, as we're doing here. For another example, the derivative of x to the power of pi would be, well, let's see, x to the power of pi, that's a power. So according to the power rule, it's pi times x to the power of pi minus 1. And there's our answer. We're going to spend some time today developing some more rules. We've got the power rule, d dx of x to the power of n equals n times x to the power of n minus 1. This rule can lead to some other useful rules. Often you'll have to find the derivative of just a plain old x, d dx of x. This is the function f of x equals x. What would that be? Well, x is x to the power of 1, so we're talking about the derivative of x to the power of 1. The power rule says we should get 1 times x to the power of 1 minus 1. That's x to the power of 0, which is 1. So we see here, according to the power rule, the derivative of x is the function 1, the constant function 1. We're going to call that the identity function rule. The derivative of x equals 1. Now actually, when we have x to the 0 equals 1, if x were 0, 0 to the 0 is not defined. So we kind of break down right there. But we've got to be careful. It turns out this does work for any value of x. And you can see that actually by looking at the function f of x equals x. It's just a straight line, linear function. Its slope is 1. The derivative of this function f of x equals x, which is d dx of x, for any x it should give us the slope at that corresponding point on the graph. And wherever you are, the slope is 1. So it makes total sense that the derivative of x equals 1. And in fact, this picture justifies it. Here's the graph of f of x equals x. Its derivative, f prime of x, is just the constant function 1. Whatever x is, f prime of x equals 1. That's always the slope at that point on the graph of f of x. Another rule that's very easy to obtain is what's called the constant function rule. It tells us the derivative, d dx, of a constant function c. This is just f of x equals the constant number c. And the derivative of a constant function is 0. And I'll show you why. Imagine that f of x is just equal to c. Whatever you plug in for x, the output is c. Its graph is just a horizontal line of slope 0. So f prime of this function would give us the slope to the graph of f of x at any number x, and the slope is always 0. So f prime of x is just the function f prime of x equals 0. Its graph is just the x-axis. So this shows you why the derivative of a constant equals 0. So now we have 3 rules. Some quick examples. What if we had the derivative of 1/3? Well, 1/3 is a constant, so this answer is just 0. The derivative of e squared, remember e is a constant, it's 2.718 approximately. You square it, you get a constant number. So the derivative of e squared equals 0. Now, notice you would not use the power rule here because it's not x squared, which fits the template for the power rule. This is the derivative of a constant, so that's 0. Likewise, if f of x is the constant function pi, if the c is pi, then f prime of x equals 0. So far we have 3 rules, and we're going to keep going with this. Let's tally those 3 rules, the power rule, the identity function rule, and the constant function rule. There are 2 more rules we'll talk about today. First of all, there's what's called the constant multiple rule. And I'm not going to work out this as a limit today. You can read this in your textbook. But what the constant multiple rule says is that the derivative of c times a function f of x is c times the derivative of f of x. It's like that c factors out of the d dx. Used in conjunction with the power rule, this constant multiple rule allows us to find a lot of different derivatives. For example, think about d dx of 5 times x to the 4. The constant multiple rule tells us that this 5 can come out of the d dx. We get 5 times d dx of x to the 4th, and the derivative of x to the 4th is 4x to the power of 4 minus 1. By the power rule, we get 5 times 4x cubed, or just 20x cubed. So here, in computing the derivative of 5x to the 4th and getting 20x cubed, we really use 2 rules. First of all, the constant multiple rule, and then the power rule. And this is typical. We're going to develop a lot of rules, and you'll typically use them in combination to find derivatives. What about the derivative of 5 over x to the 4th? Well, 5 over x to the 4th is 5x to the minus 4. So let's write it that way before we take the derivative. And we're in a position very similar to where we were up here, just the power is different. Factor the 5 out using the constant multiple rule. We get 5 times the derivative of x to the minus 4. And now we can use the power rule to find that derivative, giving us 5 times negative 4 x to the power of minus 4 minus 1. And that's 5 times negative 4 times x to the power of minus 5. And simplifying that, that's negative 20 over x to the 5th. So the derivative of 5 over x to the 4th is the function minus 20 over x to the 5th. Here's another rule that you can verify with the limit, but we're not going to do that in class today. You can read about this in the text. This is called the sum difference rule, and it tells you what the derivative of a sum or difference of functions is. If ever you have something like the derivative of an f of x, either plus or minus some other g of x, plus or minus an h of x, and so on, the derivative of that sum or difference of these functions is f prime of x plus or minus g prime of x plus or minus h prime of x, etc., when we're using the same signs here as we had in the corresponding place here. So in other words, to find the derivative of a bunch of functions added together or subtracted, just take the derivatives of the individual functions and add or subtract them in the same pattern that you had in your original problem. That's a mouthful, but it's really easy to apply. Let's do an example. The derivative of 3x squared minus 5x plus 7 would be, well, according to the sum difference rule, that's going to be the derivative of the first function, d dx of 3x squared, then minus the derivative of that second function, d dx of 5x squared, plus the derivative of the third function, d dx of 7. So now we've got three separate derivatives. We can work out the derivatives of these individual parts here using the constant multiple rule. The 3 comes out of the derivative. Likewise, the 5 here comes out. And now we can take the derivative of x squared using the power rule. That would be 2x to the power of 1. The derivative of x using the identity function rule is just 1. And the derivative of 7 using the constant function rule is 0. So we get 3 times 2x to the 1 minus 5 times 1 plus 0. And that's just the function 6x minus 1. So in short, the derivative of the polynomial 3x squared minus 5x plus 7 is the linear function 6x minus 5. And we got that so simply using these rules. If we were using the limit definition to find this derivative, we'd still be working on it. We'd be in step 3. But here you just get it almost instantly. And in fact, you can imagine that in practice, when you get to a problem like this, you can do it all in your head. You'll go straight from here to the answer. So for example, d dx of 3x cubed plus 5x squared minus 1/3 x minus 5, you would typically differentiate that term by term. The derivative of 3x squared would be the derivative of 3x cubed would be 3 times the derivative of x cubed, which is 3x squared, and that gives us a 9x squared. Next, we differentiate 5 times x squared. Well, that's 5 times the derivative of x squared, 5 times 2x to the power of 1. That's 10x. Now we have negative 1/3 times x. The constant multiple rule says the derivative of that is negative 1/3 times the derivative of x, and that's just minus 1/3. And finally, the derivative of minus 5 is 0. So in one step, we got the answer to our derivative. And it's very typical, and in fact you're going to do this time and time again, to combine these rules in your head. Maybe when you first start working these, you write down all the rules and you do it step by step, but you very quickly get to a point where you start skipping steps. That's totally normal. Get it in one step. Here's another example. Think of the function f of x is the cube root of x, is the square root of x cubed minus 1 over x squared. F of x equals square root of x cubed minus 1 over x squared. Let's find the derivative of that. Now when you look at this function, the two individual terms, they're both powers. The square root of x cubed is x to the power of 3/2, and the 1 over x squared is x to the power of minus 2. We're going to want to write f of x this way in terms of powers rather than radicals and fractions, so that we can find f prime by using the power rule twice. Now, of course, we're also using the sum difference rule because this is a difference of two functions. But working as we did in this previous example, the first thing we do is take the derivative of x to the power of 3/2. The power rule says that's 3/2 x to the power of 3/2 minus 1. Then we have a minus, so we'll have a minus there, times the derivative of x to the minus 2, and the power rule tells us the derivative of x to the minus 2 is minus 2 times x to the power of minus 2 minus 1. So cleaning this up, we get 3 halves x to the power of 1 half. 3 halves minus 1 is 1 half. Minus times minus is positive, and then 2x cubed, x to the power of minus 3. Converting this x to the 1 half back to a radical and taking the power of minus 3 down to the bottom, we get an answer. Our derivative f prime of x is 3 halves square root of x plus 2 over x cubed. And isn't that nice how we got this answer so quickly and efficiently without a limit? Now, if this were a test question and you were in my class and you gave your answer as this without converting to a radical or bringing the negative power down, that's fine. This is an answer too. I would simplify this stuff. Minus minus is positive and so on. Go ahead and simplify that. But here, this is a perfectly fine answer. Either way, we've got our derivative. So I hope you're seeing at this point that with our 5 new rules, there are a lot of functions we can find derivatives of very quickly without using limits. But there are a lot of functions that we can't find derivatives of now. What about the derivative of x cubed plus 4x minus 3 over x squared plus 1? Well, in order to apply a rule, your function has to fit the pattern. And this is not a sum or difference of functions. It's not a power. It's not a constant. It's one complicated function divided by another complicated function. We actually don't have any rule that tells us how to find the derivative of a function divided by itself. So there's no rule for this yet. So right now we can't find this derivative. There's no rule yet. Now we will come up with the rule in a couple of lectures, but for now we can't do it. And that's important to realize. At this point, and in fact, always when you're doing calculus, you can come up against functions that you have no rule for. So for this one, you might say, well, should we use the limit? The limit definition of the derivative of this function? What would that be? d dx of this function would be the limit as h goes to 0 of that function with x plus h plugged into it, minus that function, whole thing divided by h. Do you want to use this? Do you want to work out this limit? Maybe not. However, as we go on, we'll certainly never work out a limit like this ever again, but we're going to come up with rules that bypass this limit, and you'll be able to get the answer to this derivative in one step. Just stay tuned. That's in a future lecture. So in conclusion, we have started our list of derivative rules. The derivative of a constant is 0. The derivative of x is 1. The derivative of x to the n is n times x to the power of n minus 1. The derivative of a c times an f of x is c times the derivative of f of x, where c is a constant. And to take the derivative of a sum or difference of 2 or more functions, just take the derivatives of those individual functions and add or subtract them together as they were added or subtracted in the initial problem. So 5 rules, and we're going to add to our list of rules as we go along. Next time, in lecture 18, I'm not going to introduce any new rules, but we're going to kind of hit the pause button here to take a breather. We're going to look at some instructive examples. Some examples that fit patterns that you're going to be using throughout your study of calculus and beyond it, if you keep going with this stuff. So that's next time, lecture 18. For now, start getting some practice A lot of these problems are instant gratification. They're really simple. Every once in a while you'll reach a temporary stumbling block where you'll figure out how to do it. That kind of mental exercise is essential. We'll build on that. Things will become a little more complex and layered. But for now, they should be fairly easy. So be refreshed and encouraged by that. Work those examples, work those exercises. And I'll see you next time. Goodbye.